Hi, I am here to talk to you about section 12.2 in the book. Um, it's called Inference for Two-Way Tables. It's just another chi-squared test. So let's get started. So let's start with a quick example. Does background music influence what customers buy? One experiment in a European restaurant compared three randomly assigned treatments: no music, French accordion music, and Italian string music. And then under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. Our null hypothesis is going to be that there's no difference in the true distribution of entrees ordered at the restaurant when the different types of music are played. And our HA would be that there is a difference in the true distribution of entrees ordered at this restaurant when the different types of music are played. So in other words, basically, the music is influencing what type of people or what type of entrees people ordered. It doesn't state that each distribution is different from the others. It just says that there is a difference. So we don't know. We're not saying that no music is different than French music is different than Italian. We're just saying that there is a difference. There's some type of a difference. So here's the data that we've collected. We have a two-way table here. We have two variables, the type of background music being played and then the type of entree being ordered. And so if you look, these are conditional distributions. So over on the far left, for example, this is for when no music is playing, which in the table is right here. So if no music is playing, 30 out of 84 people ordered a French entree. That's about 35%. 11 out of 84 ordered an Italian. 43 out of 84, which is close to 50%, ordered something different. So the French and then the Italian music is there, right? So does it look like there's a difference? It looks like there is, but we've talked about this lots and lots. Is that difference statistically significant, or is it just because of sampling variability? If I were to do this again with another 243 people, would I have different results? So the question is, do the differences in these distributions provide convincing evidence? In other words, statistically significant evidence that background music affects customer behavior. So, like we said, you could compare many different pairs of proportions, but if you do that, you have a greater chance of making a type 1 error in at least one of the tests, because you're going to end up doing lots and lots of different tests. So what we do is we perform an overall test to see that if there's convincing evidence of any difference at all. And then if the overall test shows that there is convincing evidence of a difference, then you can do some follow-up analysis. So again, with every hypothesis test we do, we always assume that HO is true. We assume that there's no difference. So if there were no difference, then the proportion of French entrees ordered under each music condition should be the same, right? So we had a total of 99 French entrees ordered out of the 243 people surveyed, and that was 40% of all the entrees were French. So across all the different music categories, we should have 40% of people ordering French entrees. So if I look at the people who listen to no background music, there were 84 total entrees ordered. So 40% of 84 is 34 entrees, 34.22 entrees. So that's what we would expect. That's how many French entrees we would expect if no music were playing. So our expected counts now, here's the formula to calculate expected counts. Our expected counts can be calculated by so this expected count is the row total times the column total divided by the total. So 99 times 84 divided by 243 is equal to this, okay? And notice that these don't have to be whole numbers because they're expected values, they're expected counts, right? Okay. So this just kind of talks about that. So our chi-squared test statistic, just like before, and this is just right off your formula sheet, right? Remember, this is kind of at the bottom of the front page, so you don't have to memorize it or anything like that. But chi-squared test statistic is the summation of all the observed counts minus their matching expected counts squared up, and then you're going to divide by the expected count and then add those all up. Keeping in mind, this summation is over the cells in the two-way table. It's not including the totals. So if I go back a second, just quickly, it's for these cells in the table. It doesn't include any of the totals, right? Because the totals are recounting, these totals are all recounting what's already in the table. Okay, so just keep that in mind. Okay, so in this example, remember, you don't have to write out all of these, but you should at least write like the first and the last. I don't even need to write that one. I would just write first, ... last. So my chi-squared test statistic, and your calculator is going to do the number crunching for you, but ends up being 18.28. All right, so let's look at another example. So for a class project, Abby and Mia wanted to know if the gender of an interviewer could affect the responses to a survey question. So the subjects in their experiment were 100 males from their school. Half of the males were randomly assigned to be asked, would you vote for a female president, by a female interviewer, and the other half by a male interviewer. So the table shows the results. Here's your two-way table. We have the 100 subjects randomly assigned to different groups, and 50 of them were asked by a male, 50 by a female, and here's the results, right? So we need the null and alternative hypothesis. Remember, you're not going to do this in symbols. You're only ever going to use words for chi-squared tests. So HO, there's no difference in the true distribution. So again, it's about the population of response to this question when asked by a male interviewer versus when asked by a female interviewer. And then HI is that there is a difference in the two true distributions of response to this question between the male and female interviewer, right? So now we need to do the expected count for the male yes cell. So that's just this cell right here. So this is the observed counts. These are the observed counts. Now we need to calculate expected counts. So remember, our expected count is the row total, the column total, multiplied together, divided by the total. So in this case, we get 34.5. And your calculator is actually going to help you find these expected counts as well. You'll see in a couple minutes. But you need to know that formula. You need to know how those things are found. Notice all the row totals and column totals still add up to the same, right? Okay, so then we need to calculate the value of the chi-squared test statistic. Remember, the chi-squared test statistic is ignoring this. So we basically have like 6, 1, 2, 3, 4, 5, 6 like pieces or things that you're summing at the end of it, right? So we have our observed count minus our expected squared divided by our expected in each of these 6 cells. So our chi-squared test statistic ends up being 4.25. Now let's talk about conditions. So these conditions are going to look real familiar. Random, 10%, large counts. So random, we need independent random samples, or we need the random piece to come from an experiment that was randomized. So randomly, subjects were randomly allocated like they were in the previous example. The 10% condition, remember, we don't use that when we have subjects that are randomly allocated, only when we have SRSs. And then our large counts, remember this a hypothesis test is assuming always that HO is true. And if HO is true, then your expected counts are true. So your large counts condition is that the expected counts all have to be at least 5. So in this case, here's just a recap of observed and expected counts. We calculated our chi-square test statistic to be 4.25. Now we're going to check conditions, calculate a p-value, draw a conclusion. So conditions. So in this case, we didn't take separate SRSs. Remember, they did an experiment where they had 100 subjects. I think it was 100 male, right? 100 male subjects, and they randomly allocated them into 2 groups and 50 in each. So 50 people were interviewed by a male, 50, actually I should be over here with the observed counts. 50 were interviewed by a male, 50 by a female, right? So the treatments were randomly assigned. So I don't check the 10% condition because I didn't do an SRS, right? So that's down here. And then I need to check expected counts. They're all at least 5. So those are my conditions. Now we need to check the p-value. So here's your chi-square test statistic. So your degrees of freedom in this case are going to be the number of rows minus 1 times the number of columns minus 1. So in this case, we have 3 rows, 2 columns. So our degrees of freedom is going to be here, 3 minus 1 times 2 minus 1, which is 2. So you can look up the table, 2 degrees of freedom, and look over. So you're on the 2 degrees of freedom row, and you're going to look for the value closest on that row to 4.25. And you're going to see that the p-value is somewhere between these 2 numbers. Or you could use the chi-squared CDF function on your calculator and get that the p-value is 0.119. So here's your picture that kind of goes along with that. Oh, quick reminder, notice your chi-squared distribution is always right skewed, and it always starts at 0. Can't ever go below 0, right? Okay, so we want to interpret the p-value. Remember, with the p-value, you're always assuming that the null hypothesis is true. So in this case, if we assume that the gender of the interview doesn't affect the responses, there's a 0.11 probability of observing differences in the distributions as large as or larger than what happened here just by chance alone. And then what conclusion would you draw? So our p-value is 0.119, right? If our alpha is 0.05, our p is greater than alpha. We fail to reject HO. We don't have evidence of a difference in the true distribution of response to this question when asked by a male versus when asked by a female. All right, so listen, there's obviously a lot of math involved with like the chi-squared test statistic and things like that. So as always, your calculator is going to do all that number crunching for you, okay? Now, I can't unfortunately record on this video how to use the calculator, but this is a little bit more complex. So you're going to have to, your data is in the form of a two-way table. So the way you enter that two-way table into the calculator is by using what's called a matrix. Now, I'm just going to kind of click through these slides and I'm going to refer you to the book. If you look in the book on page 787 through 788, it gives you kind of like detailed directions on how to use a matrix and how to do this test, okay? How to enter the data, all that stuff. But so here's, let me flip through here. So you're going to enter, you're just going to enter your, here you're entering your observed counts. That's the only thing you need to enter. From there, you go select the chi-squared test. This is, remember, chi-squared GOF, that was the chi-squared goodness of fit test. That was 12.1. This is just the chi-squared test. So your observed counts are in matrix whatever. I always just use matrix A. And I always keep these the same. And then it's automatically, when you hit calculate, it's automatically going to, spit whatever your expected counts into matrix B. Okay. So, and then when you hit calculate, it's going to give you the value of the chi-squared test statistic and your p-value and your degrees of freedom. And then after you do all that, if you go back into your matrix function in the calculator, and if you go into matrix B or wherever you selected here for the expected counts, it automatically kind of populates the expected counts for you. So it does all that number crunching. Remember that formula, like row total times column total divided by the total for each cell. So you don't actually have to do that math. So kind of like with other tests that I've told you, I enter my data into the matrix, I do the test. So I kind of like have all this information with me first, and then I start writing down, my conditions, and because this expected counts has to be a part, and you'll see in a second too, but that's a part of your work. You have to have that expected counts to a table down on the paper, okay? All right, so kind of like before, you always have to have degrees of freedom. That has to be a part of your response as well. Your chi-squared test statistic we already talked about. You don't have to write out every cell, just first, ... last. That's fine. All right, let's look at another example. So the Pew Research Center conducts surveys about a variety of topics in many different countries. In one survey, it wants to investigate how residents of different countries feel about the importance of speaking the national language. Separate random samples of residents of those countries were asked questions, including this one. Some people say that the following things are important for being truly whatever. Others say they are not important. How important do you think it is to be able to speak English? So here's the observed counts, right? So a total of 3,463 people were surveyed. And you can see the results. So do these data provide convincing evidence at the alpha equals 0.05 level that the distributions of opinion about speaking English differ for residents of those three countries? All right. So first thing I would do is, like I said, before I do anything else, get this into a matrix in my calculator. And then I go through and I do the chi-squared test so that I have everything on my calculator kind of ready to go for me. But after I do that, we need to state our hypotheses, right? So HO, there's no difference in the true distributions of opinion about speaking English for the residents of the different countries. And then HA is that there is a difference. Remember, always in words, in context, there's really no shortcut here. And you should definitely never, ever, ever use symbols. Okay, so conditions. Remember, random, 10%, large counts conditions. So they told us that these were 3 different independent SRSs. So that's your random condition. Because they were SRSs, we need to check the 10% condition for each random sample. Remember, there were 3 different random samples. So we checked the 10% condition of Australian residents, UK, and US, right? And then our large counts condition, remember, we're not doing large counts on this. We're doing it on the expected counts. So remember, I told you a minute ago that I have this, this data in matrix A. I already did the test. So I'm going to go into my calculator matrix B and just copy down the expected counts. Yes, this table, I know this is annoying. It feels like it's a lot of work, but yes, you do have to write this down. This needs to be on your paper, no questions about it. So anyway, the third condition is that all of these expected counts are greater than 5. All right, so now I have my conditions. Now it's time to calculate your chi-squared test statistic. So we have at least 2, of these pieces in here. You use the ... Remember, your calculator does the number crunching for you. You're never actually typing this stuff in. So your chi-squared test statistic is 68.57. Degrees of freedom. Remember, number of columns, minus 1. So 2. Number of rows, minus 1. So the degrees of freedom is 6, right? You have to write that down. That looks like less than. It should be equals to, sorry. So degrees of freedom is 2 minus 3, which is 6. And you're going to draw your picture and you're going to use your calculator and it'll give you a value like whatever times e to the negative whatever. So in other words, you have scientific notation. This p-value is teeny, teeny, tiny, like very close to 0, right? So we need to draw a conclusion. So the p-value is really small, approximately 0, obviously less than alpha. We're going to reject HO and say that we have strong evidence because our p-value is so small. You can even say we have very strong evidence that there is a difference in the true distributions of opinion about speaking English for residents of Australia, UK, and US. So remember, the smaller p is, meaning, the smaller that p is means the more strong your evidence is. All right? So, again, expected counts. I'll say it again. You need to have them written down. That table needs to be there. Okay, here's another question for you. Are people who are prone to sudden anger more likely to develop heart disease? An observational study followed a random sample of 8,474 people with normal blood pressure for about 4 years. Each person took the Spielberger Trait Anger Scale test. Researchers also recorded whether each individual developed coronary heart disease. So here's your results. This is their, whether or not they have coronary heart disease, and this was their anger level according to this Spielberger Trait Anger Scale test, right? So over here on the right, we're looking at people just with the CHD, the coronary heart disease, and we're looking at the percent of people with each anger level. So does it look like there's a relationship? Maybe, right? But is this statistically significant? Is there a statistically significant relationship? That's the question. All right, so HO and HA. Now we're saying that there's an association, we're trying to prove that there's an association between anger level and heart disease status. In the population, again, it's about the population, not just in the sample. So HO is that there's no association. HA is that there is an association. Again, this is in words, in context, no symbols, no numbers, nothing like that. Another way of saying this is that if there was not an association, those two variables would be independent. If there was an association, those two variables would not be independent. So kind of like two ways of saying the same thing. So now we're really talking about independence. All right, so expected counts. If we imagine choosing one of these people at random, the probability that they had the coronary heart disease would be 190 out of the total, right? So if we assume that HO is true, that those two variables are independent. Remember, independence, our chapter on probability. If two things are independent, then the probability of B given A is just equal to the probability of B, and vice versa. So the probability of yes given low anger should just be equal to the probability of yes, right? So of the 3,110 low anger people in the study, we would expect, 0.02242 of those 3,110 people to get CHD, or in other words, your expected count would be this. And remember, expected counts don't have to be whole numbers because that's what they are, expected counts, they're averages. So again, here's our formula for expected counts. Row total times column total divided by total total. So if we go through the whole table, these are our expected counts. Conditions. This is what's called a chi-squared test for independence. So we're seeing if the two variables are independent or not. the conditions are the same. The data come from a random sample, 10% condition when sampling without replacement, and large counts condition, again, is on the expected counts, and those expected counts all have to be at least 5. Chi-squared test statistic is the same. Degrees of freedom is the same. Number of rows -1 times the number of columns -1. Let's look at an example. So this was an example that we looked at all the way back in chapter 1. Not that I expect you to remember it, but just as a quick recap, we have a random sample of winter visitors to Yellowstone National Park. They were asked 2 questions. Do you belong to an environmental club, and what's your experience with a snowmobile? So here's our results. Do these data provide convincing evidence of an association between the environmental club status and the type of snowmobile use? So I want you to make note that this was an SRS. So we did an SRS. This was, and we asked them a survey. Like this was not, this was one SRS, and we asked questions to each individual person. This was not an experiment in which I had people randomly allocated to 2 different groups or whatever, right? And we'll talk more about that in just a second, but why I'm pointing that out. So the question is, do the data provide convincing evidence of an association between environmental club status and type of snowmobile use? So HO, they're asking if there's an association. So HO would be that there's no association. You assume that there's no association in context. HA is that there is an association in context. That's what we're trying to prove. I don't think they gave you an alpha, right? So you can use whatever alpha you want. 0.01, 0.05, 0.03 if you want to be crazy, as long as you write it down. So we'll use 0.05. This is what's called a chi-squared test for independence, because remember, if I go back a second, if we're saying that there is no association or there is an association, we're asking about independence. Are these 2 variables independent or are they not independent? All right, so they told us it was a random sample. Because it's a random sample, we need to assume, or we can assume, that 1,526 is less than all, or 10% of all the visitors to Yellowstone. And then we need to check expected counts. Remember, I would have already put this into the matrix A, used my calculator to do the chi-squared test, not chi-squared GOF test. And then your calculator does all the number crunching for you. It does the expected counts for you. So you have to draw this table, or you have to write this table down on your paper, but your calculator does all the work. You're just copying it out of matrix B or wherever, you selected to put for the calculator to put these expected counts in. So all these counts are greater than 5. So our conditions are met. So chi-squared test statistic, you're only writing down 2 of these at least. You use the ... You get 116.6 degrees of freedom. There's 2 columns, 3 rows. So 3 minus 1, 2 minus 1 is equal to 2. And then your p-value, I would just use the p-value that they give you in the calculator when you do your chi-squared test. You have your picture, right? And then just like we have been doing, compare your p to alpha. So your p is essentially 0, which is less than alpha. Therefore, we reject HO. And again, because that p is so small, we have strong evidence of an association between the environmental club status, whether or not they're a member, and the type of snowmobile use in the population of all winter visitors to Yellowstone Park. So a couple things to point out. This is in context, and it's also about the population of all the winter visitors, not just what happened. We know what happened in the sample. I don't care about what happened in the sample. I already know, right? I'm making a projection about the population. Okay. So just another reminder about p-values. Your p-value is a probability, so it's going to be a number between 0 and 1, right? Or like 0 and 100%. So if you see like 1.25 on the calculator, it'll be like e to the negative whatever, so it's really scientific notation. All right, so let's talk. I kind of tried to point this out throughout the examples that we looked at. We really have two tests, the chi-squared test for homogeneity and the chi-squared test for independence. So they're essentially the same test in terms of like the mechanics of the test. The names are just different based upon how the data were produced. So if the data come from two or more independent random samples, or if they're treatment groups in a randomized experiment, you're doing the chi-squared test for homogeneity. That's like the restaurant one. You have three different, conditions, let's say. You have three different like music situations or scenarios or whatever happening. And from the three different music situations, you independently count how many people ordered a French entree or an Italian entree or whatever, right? On the other hand, on the snowmobile example that we just looked at, we had one SRS. It was just one SRS. And then from that SRS, we asked, we recorded data on two variables, whether or not they used the snowmobile and whether or not they were in that club, right? So that would be a chi-squared test for independence. So from that one SRS, are the two variables that were recorded, are they independent? All right, so look at another example. So are women and men equally likely to suffer a lingering fear from watching scary movies as children? Researchers asked a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they awake. The following table breaks down the results by gender. So assume that the conditions for performing inference are met. Minitab output for a chi-squared test using these data is shown. So you should be familiar with what this looks like, what I'm about to show you, because sometimes you're not going to be actually doing the test. You'll be given the output and you'll be asked questions about it. So ready? Let's take a look. Let's see what it looks like. So look at this carefully, read this carefully. It's always going to kind of give you information. Expected counts are printed below observed counts. So look, male, female, yes, no. So expected counts are printed below observed counts. All right, so here's observed, 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 expected, 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 right? And then it says chi-squared contributions are printed below expected counts. Below expected counts, chi-squared, 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 chi-squared. So when you add up these four numbers, 1, 2, 3, 4, when you add up those four numbers, you get the chi-squared test statistic, which is this thing right here. It tells you degrees of freedom, but you could have figured that out. You have two rows, you have two columns. So 2 minus 1 times 2 minus 1. So 1 times 1 is 1, right? And then it also gives you the p-value. And I neglected to mention we have like our totals. Total, right? So that's kind of like what you can see here in the table. Let me kind of erase this here. Hold on. Oh no. Why can't I erase? Okay, never mind. I'm not erasing. Sorry. All right, so the question is, should a chi-squared test for independence or should a chi-squared test for homogeneity be used in this setting? And explain your reasoning. So think about how the data was produced, right? Remember, that's the question that you need to answer. Researchers asked a random sample of 117 college students to write the narrative accounts of their exposure, right? So how many SRSs did we do? We did one SRS, and then from that SRS, we categorized people according to gender and according to like how they answered the question, right? So we're trying to say, are these two variables independent? So we should do a chi-squared test for independence. All right, so state an appropriate pair of hypotheses. So HO, remember HO is you're assuming that there is no association, or in other words, that the two variables are independent, and HA is that they are not independent. So one affects the other. So there is an association in context, and it's about the population, right? So which cell contributes most to the chi-squared test statistic? In other words, which one is the most difference? What's the biggest difference? So you have to look at each of these chi-squared contributions and just pick the biggest number, right? The biggest number is this one here. So men who admit to having lingering fright symptoms account for the largest component. So they were, in other words, their expected counts were furthest away from their observed counts. On the other hand, if I look, the smallest contributor were the females who did not have the lingering fright symptoms. So their observed counts were closest to their expected counts, right? Okay. All right, so here's our p-value. They gave it to us. Interpret it. Remember, we're assuming that HO is true. So if there's no association between the gender and whether or not the college students have lingering fright symptoms, there would be a 0.045 probability of obtaining an association as strong as the one that we see or more strong. So our p-value is 0.045. If alpha is 0.01, then our p is bigger than our alpha. We fail to reject HO. And we don't have convincing evidence that there's an association between gender and whether or not college students have lingering fright symptoms. In other words, we would say that we don't have convincing evidence to say that these two things are not independent. Now, if alpha was 0.05, your conclusion would be the opposite, right? Because 0.045, it would be less than 0.05. So it all depends on where you decide to set your alpha. And that's the end of this section. If you have any questions, please email me. And thanks for watching. I would say biggest takeaway, make sure you can identify the difference between when you would use the two tests. All right? Thanks again. Have a great day.